and welcome to the variability lecture. So we've gone over central tendency, mean, median, and mode, which you guys probably are familiar with to some extent. You might not be familiar with all the different aspects of variability. Variability is essentially how data varies in a data set, hence variability. You vary how much it varies. So without further ado, let's get crack-a-lackin' up into variability. So here we are, variability. So why do we measure it? Why is it important to know how much data is dispersed within a data set? Well, we measure it because it provides more context to the mean. So typically when we talk about variability, oftentimes, especially in this class, we're going to talk about mean, which is actually a measure of central tendency, but it's going to be paired with standard deviation, which I'll cover in this video. But these two are essential to understand kind of the snapshot of what the data looks like. It allows us to know how far apart these scores are spread. There's a big difference between, if you have a mean of 5 and every single score is 5 versus if you have a mean of 5 and you have some scores that are 0, 10, -20, 30, -5, etc. So standard deviation and variability provides us the knowledge of knowing, well, are things close to the mean? Like if every single score is 5, the mean's going to be 5. So is it that every single score is really close together, or is it that all the scores are kind of spread apart, more dispersed? That's what variability gives us. So there are a few different ways to measure variability. And variability can measure or can range from 0 to God knows how high. You can't have variability less than 0. If you have a variability of 0, that's saying that every single score is the same. So like that example I said where, oh, you have a mean of 5 and every single score is 5. So you add 5 up however many times and then divide by that many times, you're going to get 5. That would be a variability of 0, meaning there is absolutely no dispersion, no spread of scores around the mean because every score is the exact same. That's 0. You can't get any more same than same. So having a variability of 0 is saying everything's the same. You can't have a variability that's negative. I don't even know what that would look like. If every single score is the same, it's just 0, that variability measure. And then in terms of how far data can spread, that can be, however far apart it spreads. There's not really a cap to how high variability can be, but there's definitely a cap of how low it can be. Again, that being 0. So there's a few different measures of variability that I'm going to go over. We're going to pay the most attention to variance and standard deviation, but I'm still going to go over range and quartiles as well as interquartile range. So we'll start with range. You guys might be familiar with this. It's just the difference between the largest and smallest values in a distribution. So you look at the scores of a data set and you take the biggest one and you subtract it by the smallest one. That is the range. This is different from the real range that we talked about when we covered histograms. Keep in mind that the real range is doing pretty much the same, taking the largest subtracted by the smallest, but then adding 1. That is the real range, which is different than just the plain range. Again, with range, all we do is subtract the smallest from the largest, and we don't have to worry about anything else. With real range, we add 1 once we've done that. So when we have range, take a look at these little tiny data sets. That first one of 1, 3, 5, and 7, the range is 6 because we're taking the largest score in the distribution, which is 7, and subtracting it by the smallest, which is 1. So we have a range of 6. The next data set, all the same numbers, except now the largest number instead of 7 is 80. So now our range is 79. So range isn't as informative as, let's say, standard deviation is, because having a range of 79, it tells you, okay, so that's the difference between the largest and smallest, but there's only really one number that in that data set that's larger than 5, larger than 10 even, and that's just that 80. So having a range of 79 makes it seem like, oh wow, maybe there's like a 20 in there, a 72. These are I'm referring to scores within the data set. Maybe there's a 7 and then there's a 52 and no. The range is just saying the largest minus the smallest. It's not saying how close these are to the mean or how close they are together. And 1, 3, 5, and then 80, they're not very close. The 1, 3, 5 are fine, but that 80 just kind of comes out of nowhere. So the range is just telling you this is how far it spreads, but it's not really giving you an idea of how close together these scores are. Quartiles and interquartile range. In this case, quartiles is when you split your data set into 4 quartiles, quart, 4, etc. Each quartile contains 25% of the data. So you have your smallest quartile at quartile 1, your middle 2 at 2 and 3, and then your quartile containing the highest range of your data at quartile 4. So what you're doing is that this is how you measure your variability. This is saying, oh, okay, so quartile 1 has numbers, X through Y, and then quartile 2 has numbers Z through B. I'm just throwing around letters now. But, excuse me. The interquartile range is looking at the scores between the third and the first quartile. So you're looking at that middle section of the data. Now this is not affected by outliers. Range is affected by outliers because again, we did that 80 minus 1 and that gave us a range of 79. So certainly outliers are going to be a factor when you're subtracting the largest from the smallest. Interquartile range though, you're just looking at the middle set of data, not paying attention to the outliers, which can be super high or super low. It's just that middle portion. So we're not really concerned with outliers when we're dealing with interquartile range. Now, this still isn't really giving us a full picture of the data. It's just, again, looking at that middle chunk. Now is where we get into variance. So variance is a measure of the average square distance that all scores deviate from the mean. So you might think, well, what does that even mean? Oh, well, we're going to get into that. So variance is not standardized because we've squared all the scores. And so when we have variance, it's going to be a lot more bloated than the original data set was. You might have a data set of 1, 3, 5, 7 and a variance of like 9 or something. But hey, how does that make sense? None of our scores are even better than or higher than 9. And we have this variability of 9. What? So the reason for that, variance always kind of seems large because we've squared all the scores. Now, it's a better measure of variability than range because it's not only focused on the biggest and largest scores, it's looking at all of them. And again, it's better than interquartile range because again, it's looking at all of them, not just the middle chunk, not the middle quartiles, but in the entire data set. So when we talk about variance, we're going to talk about, and standard deviation as well, but we have the population variance and standard deviation, and we have the sample standard deviation and sample variance. They have two different formulas, and it's important to note which one you need to use before you start calculating. So when we use population variance, this formula we use when we're dealing with a population. So keep in mind that when we're dealing with population, oftentimes it's going to say, to know that we're dealing with population, questions or problems are going to say something to the effect of, oh, we are only interested in 50 people in a class. We're not trying to generalize this to all college students or all high school students or all women or all men or whatever it is. If you say, oh, we took 50 students in a stats class and we're only interested in these 50. We're not going to generalize to, we took 50 students from a stats class to see how all stats students fared in this. No, that would be a sample because you're saying you took 50, but you're interested in all stats students. Population, you're just saying, I have this many and this is all I'm concerned with. No generalization here. So a quick thing to note with population formulas is that oftentimes they will include Greek numbers. Now that's not to say sample doesn't have that as well, but notice here, this is the formula for population variance. Now the notation that signifies population variance, which is this right here, is sigma squared. I know we've talked about sigma before as a, actually there's 2 sigmas in this. You have this sigma, which represents population variance when it's squared. And then we have this sigma, which just represents the summation, the adding it all up, essentially. But what this is saying is, in order to calculate population variance, sigma squared, you need to take each score and subtract it by the mean, the population mean, and square those scores and add them all up and divide by the total number of people in your population. Okay, so sigma in parentheses x minus mu, or population mean squared, divided by n. Again, that's just saying first you have to calculate the population mean, then you subtract the population mean from each one of your scores, square that, add all those together, and divide by the total number of people in your population. Now the numerator of that fraction, or the top number, is also known, or the top part here, is also known as the sum of squares. So this whole summation of each score minus the mean squared, that is the sum of squares, and dividing it by again, the population mean. So SS represents this information here. Okay, so we know how to calculate it. We have the formula. So now let's actually do it. So let's say that you want to see how much your 6 closest friends actually know you. You're only concerned with your 6 closest friends. Maybe that's all the closest friends you have. Honestly, I think that's a lot of close friends. But anyway, you only want to know how these 6 people scored. You're not trying to generalize them to every person you know, or, you know, every person in the world. Your only population of interest are these 6 people. It's not, again, it's not saying, and I want to generalize it to all my friends. Nope, it's just these 6 people. So you quiz them with 10 facts about you. So you give them a little test on you, and you keep track of their scores, or how many they got correct. And you want to measure the variability in terms of variance. So here are the scores. You got 5, someone, you got a perfect score, you got a 3, you got a 7, a 2, and another 3. So since these are the only people you're concerned with, you're not trying to generalize, we're going to calculate the population variance for the scores that your closest friends got on a test about you. Okay, so again, we have the scores of 5, 10, 3, 7, 2, and 3. These scores will come up again. So 5, 10, 3, 7, 2, 3. All right. All right, those are the scores that each of our friends got. Okay, so here's the formula again, where again, sigma squared represents population variance. So this population variance equals the sum of each individual score minus the population mean squared. But first, before we do that, we got to find the population mean, right? So in order to do that, population mean, sample mean, those are all going to be calculated the same way. Mean is mean. So you just add all of the scores up and divide by the total number of scores there were. So we had, remember, we had 6 of our closest friends take this test, and here's each of their scores: 5, 10, 3, 7, 2, and 3. We add all those up and divide by 6. That gives us a mean, a population mean, mu, of 5. So I'm going to write that down. We have a population mean of 5. That's what we're rocking so far. Okay. So now we get to the nitty gritty. Now we get to calculating the sum of squares. Again, that top part of subtracting the mean from each individual score, squaring that, and then adding it all up. So we had our scores of 5, 10, 3, 7, 2, and another 3. So here, I've just done this here. So again, we're subtracting the mean from each score. This x equals is each score that our friends got on the test. There are 6 scores here: 1, 2, 3, 4, 5, 6. And now we just subtract the mean from each of those scores. So 5 minus 5 is 0. That's easy. When we square that, it's still 0. 10 minus 5 is 5. When you do 5 squared, that equals 25. 3 minus 5 is -2. Square that, you just get 4. 7 minus 5 is 2 again, square that, you get 4. 2 minus 5, -3 squared is 9, and 3 minus 5, -2 squared is 4 again. So we've done this part where it says the scores minus the mean squared. We've done all that. We have 0, 25, 4, 4, 9, 4. Now we do this sigma part, which is referencing just adding them all together. So we do 0 plus 25 plus 4 plus 4 plus 9 plus 4, and that gives us 46. 46 is our sum of squares. That is the top part of our equation. 46. Cool. Keep in mind, though, we still have to do one more thing, and that's divide by the population size, which was 6. So you take 46, divide by 6, and then you have 7.67. Again, we're always going to round to the nearest hundredth or 2 decimal places. So I believe that's like 7.66666666666666666. I don't want to summon a demon, but you would just round that to 7.67. Easy. Okay, so our population variance for this data set, once we've calculated it, is 7.67. That's sigma squared. I don't draw it very nicely, but essentially, that is our population variance. Okay. Keep in mind that that is signified by sigma squared. Now, let's calculate sample variance. Everything is pretty much the same, except note how when I said earlier, you'll know you're dealing with variance or populations when you have Greek letters to signify it. So we had that sigma squared, and that represents population variance, that little curly Q squared. For sample, typically we just use normal letter. Well, I don't want to say normal letters, like one language is more normal than the other, but we use S, the letter S squared. That represents sample variance. And that's equal to pretty much the same thing. Most of this is the exact same, except in samples, it's notated a little differently. So keep in mind that mu, that little mu represents population mean. Well, now capital M, or you can do X bar, whatever, that represents sample mean. So we're still taking each of our individual scores and subtracting the mean, in this case it's the sample mean since we have the sample variance, and squaring that, adding all those scores together, and dividing by sample size minus 1. So in terms of what you're doing for variance for sample and population, that top part is the exact same. It might be written a little differently because we're dealing with samples now instead of populations, but you're doing the exact same thing. The sum of squares is still calculating the mean and subtracting the mean from each of your individual scores, squaring that, adding it all up. That's all the same. But the denominator, the bottom part of the fraction, now you're going to have to not just divide by population size, which is just everyone, but you're going to have to divide by sample size minus 1. Okay, so I'll show you guys the difference in this. So let's say we have the same thing going on. We have how well all of our closest friends know us. Maybe we have more than 6. Let's say we do have more than 6. Or if you think, I don't have more than 2 close friends, maybe just think of, generalize this to all people you know, which is, probably a lot. So you have more than 6 people that you know, but you still only manage to collect data from those same 6. So just to keep it easier, we're going to keep the same scores, that 5, 10, 3, 7, 2, and 3, just to show you the difference of how sample variance works in opposition to population variance. So we're going to use that same data, most of the same process. So we got to do the sample mean first. So it's that same thing. We add all the scores together, the 5, 10, 3, 7, 2, and 3. And we're still, when we're calculating mean, we're still going to divide by the total number of people that we have gathered information from. That's still 6. So our means are still going to be the same at 5. Just like it was for population variance, it is also the same for sample variance. The mean is 5. sum of squares will also be the same. Like I said, this formula looks pretty much, once we've plugged in the sample mean, it looks pretty much the same once we got to this point when we were calculating the sample sum of squares for populations. So it's still going to be take each score, subtract it by the mean, square it, and then add all those up. So again, take each score, the 5 minus 5, 10 minus 5, 3 minus 5, square those scores to 0, 25, 4, 4, 9, 4, add them all up, we still get 46. The sum of squares is still the same between sample and population variance. Now, this is where we start getting different. So keep in mind that it's the sum of squares divided by the sample size minus 1. So instead of dividing by 6 like we did for population, we're dividing by 5, taking our sample size of 6 minus 1. Now keep in mind, I know I'm going back and forth and saying, oh, well, 6 was our population size for population, and now 6 is our sample size for this question. Keep in mind, it's all in the wording. In the population variance question, it said, we are only interested in these 6 people. That's it. And in the sample question, we're using the same number of people, those 6 people, but instead of just saying, we only care about these 6, I don't care about everyone else, these are the only ones I'm interested in, we said, oh, we want to generalize this to all of our closest friends or all people we know or whatever, more people than these 6. But we only managed to get 6 people to take this test about ourselves because no one else had the patience to deal with our arrogance. I don't know. So we take, since that distinction has been made that this 6 is representing, you know, a broader scale of, we're using this to generalize to more people than who we have here. That's why this is sample. In case you're kind of wondering, well, why is now this sample size, even though this is the exact same as the last one? It's the fact that we're using these 6 people to generalize to more people. You can look over the PowerPoint and read over the differences between the population question for the friends and the sample question for the friends, if you want to kind of narrow that down more. But anywho, I digress. So we have our sum of squares divided by sample size minus 1. So our sample size was 6. 6 minus 1 is 5. So now we have a sample variance of 46 divided by 5, which is 9.2. So I'm just going to write that down. Sample variance, again, that's just signified by s squared equals 9.2, well, 9.20, I should say, but essentially. My handwriting is not the greatest, but I feel like hopefully you guys should be able to read it. But yes. So if you're thinking, okay, so what's the point of that n minus 1? Why does the sample formula why does the sample formula for variance has to go all willy-nilly and decide to be silly and go negative, or to go n minus 1? Why does it do that? Well, keep in mind what we're doing with samples. Again, we have 6 people, you know, we want to take these 6 people, but we want to know about all of our friends. Or we're looking at these 50 college stat students in Professor Cooper's class, but we want to know about all stat students at Fresno State or in California or in the United States or wherever, doesn't matter. We are using these samples of 6 people or 50 people or 1,000 people, whatever. You can have large samples, but there's still going to be a sample if you're using them to represent the entire population. If you have not gathered every single person in the population, it's a sample. So since we're doing that, since we're using these samples to generalize to a population, the reason why it's larger, the reason why we use n minus 1 is so we can do that. So you'll notice that for our population variance, it was 7.67. For our sample variance with the exact same numbers, it was 9.20. So why is the variability, the variance for samples, larger than the population? How does that make any sense? Well, it's because we have to kind of, since with samples, we don't have access to the whole population. We're only looking at these 6, but we want to know about everyone we know, or we're only looking at these 50 stat students in Professor Cooper's class, but we want to know about all stat students in California. since we don't have access to the entire population, we only have this sample of people, we have to kind of extend the reach of our guess on the variance, on how far this data is dispersed. We have to accommodate for maybe, let's take, for example, this friends test that we have, the example we've been working with and working through. We have to accommodate for, okay, well, maybe some people know us super well, so their score super high, or some people barely know us at all and they'll score super low. How do we account for that if we don't have access to the whole population? Well, variability, our variance here, we extend it. Sample variances, when you use the exact same numbers, are always going to be larger than population variance or standard deviation as well, because we're kind of guessing. We're kind of overextending our guess, so we make sure we gather and we're accommodating for everyone. It would be like if I asked you, if you talk to your parents, okay, or, you know, 6 of your friends again, whatever. But if you talk to, let's stick with your parents. If you talk to one of your parents and said, how many shoes do you have? And your parent says, oh, I have 7 pairs of shoes. That's how many I got. I just counted, looked at my closet, I have 7 pairs of shoes. And then you have to guesstimate how many shoes both of your parents have together. Well, you know you have at least 7, okay? Let's say that's your dad, I don't know. But then you're thinking, okay, so how many shoes does my mom have? Ooh, oh God, my mom has tons of shoes. I know my mom does. So if I knew how many shoes my dad had, which I don't know, he might have more than 7. But if I had to guess and say, if the rule is, if you are below your guess, it's incorrect. You know, you null and void everything. You have to overreach. So, okay, I know my dad has 7 pairs. My mom, in actuality, she could have like no more than 10. Maybe she has 10, 12 pairs of shoes, but I don't want to miss. I want to make sure I accommodate for every single shoe she has. So I'm going to guess and say she has 20 pairs of shoes, okay? I don't have the entire access to my population. If I'm only looking at my parents, my mom and my dad, and I ask my dad how many pairs of shoes he has, but I don't ask my mom, technically that's a sample. But in order for me to know exactly, okay, I want to know how many shoes you guys have combined. I kind of have to fill in the blanks with how many mom has. I'm going to kind of over guess. I'm going to have a larger estimation just to make sure I don't miss, you know, just to make sure I'm not shortchanging you guys in your total number of shoes. Same thing for sample variance. It's a little different in terms of, you know, it's more the variability, but it's the same concept. If we don't have access to the entire population, we kind of have to make that guesstimate of how far the data spreads. We have to throw that net out a little further out just to make sure we can capture all the fish of that data distribution. So why is it the sum of squares? Why do we do that whole thing where we subtract each score from the mean, or subtract the mean from each individual score, square that, and then add it all together? Well, if we just subtracted the mean from the scores and added those all up, it would just equal 0. So we have the scores here of the 5, 10, 3, 7, 2, and 3. If we just simply subtracted all of those and then added them up, that would equal 0. That would tell us with a sum of 0, if this was like, oh, let's stop here, we have our variance. 0 means there's no variability, meaning that every single score is the same, which is not true. We have a 5 and a 10 and a 3 and a 7 and a 2, and we have another 3, but still, the fact that just 2 of these scores are different, that's telling us we do not have a variability of 0. It's impossible. They're not the same. You can't say the variance is 0. You can't say the variability is 0 because, hey, they're different. So we square it because that kind of offshoots that. Once you just subtract it and don't do anything else to it, you add it all up and it's going to equal 0 every time. But if we square it, then it kind of throws that into a loop and it's like, hey, we do have variability here. So we think, I mentioned how the variance is kind of this bloated number, how it's like, okay, it's squared, and like for our data set, for example, the largest number was 10, and we had a variance of either 7.67 for population or 9.20 for sample. Well, considering that's how far the data spreads around the mean, that's what standard deviation and variance do, how far it spreads throughout the mean. It's like, well, the mean is 5, 7.67 both ways. That's like far out from 5, and that's larger than our highest number. How does that make any sense? It's because it's squared. So in order to correct that, in order to kind of re-standardize it, we use standard deviation, which is just the square root of variance. But let's do a little practice. So we have another example here. A researcher is interested in math competency in college students. 6 college students are given the math quiz, and the scores are 3, 4, 6, 8, 1, and 9. Looking at this, just reading this question, do we need to calculate population or sample variance? I'll give you a minute. Well, you can pause it because I'm going to go into it right now. So this question is saying we have 6 college students that were given this math test. Okay, so that's our size of however many people. That's how many people we gathered information from. But that first sentence is imperative to know, is this population or sample variance that we're dealing with? A researcher is interested in math competency in college students. 6 college students are given the math quiz. Well, the researcher is interested in all college students. If they were interested in only the 6, it would be more clear of that. It would say a researcher is only interested in the competency of these 6 students, but it's not. It's saying the researcher is interested in it and for all college students, but we only have 6, which is, by the way, a terrible sample size. But just for the simplicity of calculating variance, I have these small sample sizes so we don't pull our hair out. So we have our scores of 3, 4, 6, 8, 1, 9. We know that we're going to be calculating the sample variance. Okay. So I've written down the sample variance formula right here. That's what we're going to be using. All right. So what do we do first? Now let's calculate the variance. So what do we have to do first? Well, we have to calculate the sample mean. That's simple. I'm just going to use my calculator on my phone because it's simple. So we got 3 plus 4 plus 6 plus 8 plus 1 plus 9. Okay, we have 31. Divided by, we have 6 people. So we have a sample mean of 5.17 because I have 5.1666667, but we're going to round that just to make it easy. So 3 plus 4 plus 6. Yeah, just want to double check it. Okay, so we have a mean, a sample mean of these numbers to be 5.17. Cool, nifty, bitchin'. Now what's the next part? Well, now we calculate the sum of squares. So we have to subtract 5.17, our sample mean, from each of our scores, from the 3, 4, 6, 8, 1, and 9. So let's do that. Okay. So 3 minus 5 point here. I'll show you guys what I'm doing right now. I'm just taking each score and subtracting the mean from it. After I've done that, I'm going to square it. So I should actually do. Okay. So since we're going to have to square it, I just have the original calculation or the original subtraction of score of 3 minus the mean 5.17 but I just have it in parentheses and square it because we're gonna have to do that. So let's get this crack-a-lackin'. I'm gonna start with 3. So 3 minus 5.17 is negative 2.17. I'm gonna square that. I have 4.71. Now we do the next one. 4 minus 5.17, negative 1.17. Squared is 1.37. All right, mosey on down. 6 minus 5.17, 0.83. Squared is 0.69. Nice. Now we have 8 minus 5.17, 2.83. Squared, 8.0089, so 8.01. 1 minus 5.17 is negative 4.17. Squared is 17.39. And lastly, 9 minus 5.17 is 3.83. Squared is 14.67. Okay. So I have all these. And again, what I've done is subtracted the mean from each individual score and squared that. Now I'm going to add these all up. Okay. So 4.71 plus 1.37 plus 0.69, nice, plus 8.01 plus 17.39 plus 14.67. We have a sum of squares of 46.84. Once I've added all these together, I got 46.84. Now I have to divide by what? Well, this is the sample the sample variance that we're talking about. So we're subtracting, or we're taking the sample size minus 1. So we had a sample size of 6. 6 minus 1 is 5. Why did I throw my calculator away? I need to use it. So the formula we have is the sum of squares, which is 46.84, divided by 5, which was our sample size, which was 6 people were sampled, minus 1. So 46.84 divided by 5 equals, we have a sample variance of 9.37, rounded. It's 9.368, but again, I've rounded it to 2 decimal places. So we have a sample variance of 9.37. Cool. We have it. We've calculated it. Just a moment. What happened? My apologies. I had to deal with some stuff going down. Anyway, so where did I leave off? So we have our sample variance calculated at 9.37. Now, if we were to calculate the population variance using this exact same data set, maybe the researcher was only interested in those 6 college students in terms of their math competency. That variance, if it were the population, would be smaller because we have everyone accounted for. We don't have to throw out a bigger net to make sure we catch all the fish outside of the distribution, or at least, you know, the larger fish or the smaller guppies. With the population, we got all the fish in the bucket, so we don't have to worry about throwing out a big old net to make sure we capture everything that we can't even see in the ocean. Okay. So I talked about standard deviation. I talked about how it's, well, standardized. And I talked about also how variance is this bloated number that doesn't really make sense when you look at the data set and then the variance. It's like, why is that so big? Well, standard deviation is a way to correct that. So to calculate standard deviation, you just find the square root of variance. So variance, admittedly, is a pain in the ass to calculate, as we've noticed. I mean, mean's simple, just calculate mean. But then to subtract the mean from each score and then square it, add it all together, and divide it by either population size or sample size minus 1, it's tedious. So standard deviation is actually easy once you've done variance. All you do is take the square root. That's all you do. So you calculate variance, and then once you've done that, you find the square root of variance to get the population, or excuse me, to get the population or the sample standard deviation. So note that I made a point to say, oh, it's sigma squared. Notice the squared there. Well, variance is signified by square. Since we're squaring all the scores that are subtracted from the mean and adding them together, it's been squared. Standard deviation is just sigma, or it's just S in the case of a sample. When it's squared, it's the population variance or the sample variance. But when it's just sigma or when it's just S, that is going to be standard deviation. I'll also signify sample standard deviation by writing SD, just standard deviation. But just know that it's in reference to the sample standard deviation. Okay. So looking at that, knowing that, understanding that about standard deviation, that it's just the square root of variance. Well, when you have population variance, like we had before, when we did the problem in the beginning with the 6 friends, and those are the only 6 people in the world we cared about. We didn't care about generalizing these 6 to everyone. That population variance was 7.67. So to calculate standard deviation, we just do the square root of that, which is 2.77. Put that in your calculator. Square root of 7.67 is 2.77 rounded. So the population standard deviation is 2.77 for this problem, for the friends question. Now, looking at the sample, when we did the sample variance for the same set of numbers for those same 6 people, but now we want to generalize it to everyone we know or all of our closest friends, that sample variance was 9.20. Square root of 9.20 rounds to 3.03. So our sample standard deviation for that is 3.03. Again, it's still larger. We still have a standard deviation that is larger for a sample variant, or for a sample, than it is for a population. Still kind of that same concept of we want to account for everyone. With population, we don't have to worry about accounting for people who aren't there. If we're calculating population standard deviation or population variance, everyone we're interested is right there. So we don't have to throw out a bigger net to capture the fish we can't see, the people in the population we didn't measure. Because when we're looking at population variance or population standard deviation, we have them all there. We got a bucket, or the net, we don't need to throw it super wide to span out super far. For samples, we do need to get that bigger net out from underneath the poop deck, or well, in the poop deck. But anyway, I don't know why I'm making so many sailor references, but I feel like this kind of is helpful. For samples, we want to get a larger net. For sample standard deviation, sample variance, we get that larger net to throw out because we can't see the fish. Maybe they're deep down. We just need to catch as many fish as we can. So we throw a bigger net to capture all the ones, even that we might not be able to see. We're throwing a bigger net. We're having a larger standard deviation to capture all of the data that we can't see, meaning to accommodate for the people in the population. We only have 50 college students, but we're interested in all college students. Well, there's a hell of a lot more than 50. So we're going to have to throw a net to kind of accommodate for all the millions of college students that we don't have in our sample. Hence why sample standard deviation, sample variance, or just sample measures of variability are always larger than the population. So why the hell does this matter? I've gone on this long ass rant about why population variances are different and than samples, and it's all, oh, it's really important, and oh, like, yeah, variability is important. So why does any of this matter? What the hell is standard deviation telling us? Well, we can apply standard deviations directly to a distribution. Since it's standardized, variance, remember, was bloated. It was huge, 7.67, when the largest number in our data set is 10, and that's supposed to measure variability. What the hell is going on here? But that standard deviation of 2.77, that's more manageable. So when we have this standard deviation, this is referring to how far the scores stray from the mean. And I know that 2.77, it's like, well, what do you mean it's straight? It strays from the mean 2.77? I don't freaking get it, dude. What does that even mean? What? Huh? Calm. I got this. So the smaller your standard deviation is, before I get into more of that, let me just say that the smaller your standard deviation is, the closer the scores are bundled together. Again, if you have a variability or a standard deviation of 0, that means every single score is the same. But if you had a standard deviation of 1,000, that means the scores are certainly not all close to the mean. They're kind of sprayed all over. So where does standard deviation come in when it comes to giving us information in a distribution? Well, the empirical rule states that if we were to put any sample on a bell curve, on a standard normal distribution curve like this, standard deviation is telling us that 68% of all the scores are going to be within one standard deviation of the mean. That's one standard deviation above, one standard deviation below. So we look at our data set. Granted, we have a very small data set of 6, but with our standard deviation for, let's say, the sample being 3.03, our mean was 5. That's saying 58% of the scores fall between 5 plus 3.03, which is 8.03, and 5 minus 3.03, which is 1.97. Yes. Okay, just had to make sure. Anyway, so that's saying that between 1.97 and 8.03 for that data set of our friends, the same one we've been working with, 68% of all our data is lying between the values of 1.97 and 8.03. Now, this isn't always the case. I mean, we could actually have more than that, depending, but we also have a small sample size, so keep that in mind. Once we kind of buff this out a bit, once we have a larger sample size, the empirical rule is better for that. But it's saying that 68% of all the scores in this distribution lie within one standard deviation above and below the mean. 2 standard deviations above and below is 95% of all the data, and 3 standard deviations above and below is 99.7% of all the data. So a large majority. So standard deviation is kind of telling us, hey, this number is kind of telling you how far the data spreads. So, you know, between 1 standard deviation above and below, that's where a majority of the data is. 68% is certainly a majority. And as we stray further and further from the mean, as we stray further using standard deviations as our markers of 1 above, 1 below, 2 above, 2 below, 3 above, 3 below, we're pretty much accommodating for most of the data set. So the empirical rule, you can also see it as the 68, 95, 99.7% rule, but the empirical rule is a hell of a lot easier to say and, you know, just faster. But this is exactly what the empirical rule is stating, that 68% of the data lie above and below one standard, or 68% of the data are within one standard deviation of the mean, one standard deviation above, one standard deviation below. 95 is 2 standard deviations of the mean above and below, and 99.7 is 3 standard deviations from the mean above and below. Okay, so in order to kind of mentally kind of think of standard deviation a little bit better, I'm going to give you a different sort of example where, let's say you're scrolling through your Instagram or whatever social media you get, whatever, I don't care, it's up to you. Or maybe you don't have social media, that's not my business. Anywho, so let's say you get a DM from someone and they are a sales rep for LuLaRoe, which is a women's legging distributor. Or if you don't give a crap about women's leggings, insert any sort of thing you have any sort of interest in here. Or maybe if you don't have interest, that'll make it even better. I don't know. But let's say this sales representative slides in your DMs and says, oh my God, I love your style. You're like the cutest I've ever seen. How about you make your style even better by like selling our products? You can make, our sales team made an average of over $100 a day. That could be you. You could be making so much more money. You can be, you know, getting the stuff you want. You can just live the life you want. You can, you know, upgrade into our sales program and you can get this pink car, or like, I don't know, whatever. I don't know what their deals are. But anyway, this is saying, oh, you can make over $100 a day. Since our sales team, on average, that's what they earn. That could be you. And so you're thinking, ooh, I want to make over $100 a day. That sounds nice. That'd be a nice little side hustle for me. That'd be cool. However, one thing that this person is not telling you is that the standard deviation of this distribution, this average that they're saying, the standard deviation of the sales team was 323.14. So, interesting. So we have an average of over 100, but a standard deviation of 323.14. What is that telling you? Well, it's saying, keep in mind that the smaller standard deviation is, the closer those numbers are to the mean. So if that standard deviation was a lot smaller, it'd be more likely that people are making about $100 a day. But with the standard deviation that high, that's suspect. I don't like it. Let's kind of dive in a little bit. Okay, so you do some digging and you find the data set that this person is talking about in terms of their sales reference, or their sales people in terms of their average. So you see that each point in the data set represents the amount of money that their sales team earned in one day. So one person earned $20, another 25, another 18, 32, 35, 42, 25, 52, 1,000. Someone was standing outside a yoga studio or something selling these leggings or something. I don't know. But that person who made $1,000, clearly that's not really the norm. You see a lot of people floating around, the $30-ish region. You got 20, 25, you got a 32, 42, 52. But that one person who made $1,000 in a day, they screwed up the mean as well as the standard deviation. So with this data set, yes, the average still is 138.78. So they're still earning over $100 a day on average. That is correct. But it's because of that person who earned $1,000 that threw that mean in there. So with that standard deviation being as high as 323.14, that's telling us, okay, so yes, the mean is 138.78, but since we have such a large standard deviation, you can see that a lot of our scores are not even close to $138. There's only one score that's over it, and that's the one that screws up the mean in the first place. Every other score, every other amount of money that each individual salesperson made in a day is almost $100 less than the mean of 138.78. So that sales distributor said, you can earn over $100 a day because she was looking at the mean. However, failed to represent failed to represent the truth of the distribution by including the standard deviation, which they wouldn't, because why would they? It's a scam. They're not going to do that. You're not going to want to realize, actually, people are making under $100 a day. They're saying on average I can earn that, but no, I can't. That's garbage. So the person who earned that $1,000 ruined everything. They jacked up the mean. They also jacked up the standard deviation. But that mean sounds so enticing. Oh, you can earn an average of over $100 a day. So when you remove that one person, when you remove that person who earned $1,000, the mean is actually $31 a day. The average that each salesperson made in a day was about 30 bucks. That's not as sexy of a sales pitch to say you can earn just over 30 bucks a day if you take all this, if you take responsibility for all this product that we've unloaded on you, make sure that you sell it. Otherwise, you're being held financially responsible for it, but you can earn over 30 bucks a day. But also notice that when we removed that $1,000 person, the standard deviation is sliced from over 300, from 323 something to 11.59, just under 12. This is saying, hey, the scores in this distribution are a lot closer to 31, a lot closer to the mean than the scores in the previous distribution, where the mean was 138 and the standard deviation was 323. It's a lot different. It's a lot better now. So now, the magic of distribution. That disparity of the 11.59 for when we removed the outlier and the 323 when we kept the outlier in, that's telling us that, hey, the larger this number is, the more the data is spread, the more we have to account for that person who made $1,000. That's why this standard deviation is imploded to 323. But when we take it out, when we sliced it, when we took it out, it's barely under 12 now. Cool. So the lesson of the day is knowing and understanding standard deviation can save you from being swindled by people you went to high school with 20 years ago. By throwing all your time and effort into this pyramid scheme that's not really going to make you more money. It's actually, you know, maybe some people make money that you could be that $1,000 person, but you're more than likely not going to. So don't do it. Well, I mean, I'm not going to tell you what to do, but essentially, anywho. So I hope this helped you understand a little bit more about standard deviation and variance. Again, everything we talked about today are measures of variability. So again, that refers to how much data varies in a data set. We talked about that with standard deviation, with variance, with interquartile range, and with regular range. But again, like I said, we're going to be focusing mostly on variance and standard deviation in this class, since they're more accommodating for the entire data set. As per usual, if you have any questions, stop by my office hours. I hope this video was helpful for you in terms of understanding variance and standard deviation. I know those are some topics that students tend to kind of struggle to conceptualize, but I hope my examples helped you kind of put it more into terms with my fishnets, oh man. Well, yeah, my nets that you gather fish with, not to be confused with fishnet stockings, which you could be selling with LuLaRoe or LuLaRoe, whatever. Anyway, I'm gonna stop talking before I dig myself into an inappropriate hole. So, again, if you have any questions, just contact me through my office hours or my email or what have you. I hope this video finds you well, and goodbye. Like and subscribe if you're so inclined.